to constant beam width beamforming. Okay, so what you can do, we did some work on that. So you can use my website. Let me see if it's here. Okay, if you go to my website, it's israelcohen.com. Okay, israelcohen.com. So you can go to publications, journals. I don't have it here. Just a minute. Okay, so if you go to publications, journals, and actually if you write constant, I think you can get many publications about constant beam width and so on. But what I recommend is to go to this. This is a very nice paper, which is a window-based constant beam width beamformer. Actually, based on what we talked about beamforming, you can already read this paper based on your knowledge from what I wrote about the overview. And if you're interested, it will be a very nice way to see, because I assume you have the background for signal processing and you know about sampling and so on. So I recommend that you try to read this paper about constant beam width beamformer. So it was published, you see, in 2019. So even though it's 20 pages, many are the references and so on, I think you can try to read it and see if you understand. I think you are supposed to understand this paper already based on the overview, okay? Because it's a simple way to do, and it's much nicer than the subarray method that we used before. And if otherwise, afterwards, if you're interested and your research is related to such things, you can go to more sophisticated papers with constant beam width beamforming. For example, this is also a nice paper with constant beam width beamforming with concentric ring arrays, which is interesting. And we did also things with non-uniform sensor arrays and so on. But this one is quite simple, the first one which I mentioned. Any other questions that we have so far? Okay, so let's continue. So we defined performance measures. Now we want to optimize, to find optimized filters in order to improve or based on this criteria. Okay, so the simplest or the most common optimal filter, it's known as Wiener filter. Wiener filter, what it tries to do is to minimize the mean squared error, what we defined before. So the mean squared error contains two errors. One, the error which is related to the distortion, and the other error is related to the residual noise. Okay? Okay, so we said that Z equals to X filter desired plus residual noise. So if we take Z minus X and we take that squared. So this is the squared error. And if we take the expectation of this, this is the mean squared error. So this is the mean squared error, which depends on H, on the vector H. So the filter that minimizes this mean squared error is called the Wiener filter. And the question is if it's good or bad. So it depends on your application. Sometimes it's good, sometimes it's not good enough, because the mean squared error, it doesn't mean that the performance is good. It just minimizes the mean squared error. I can show you examples either for speech signal or for images. You look at the image, the mean squared error of two images with one. The mean squared error is lower, but it looks worse than the other image. So not necessarily minimizing the mean squared error is the best option. Sometimes it depends on the application, because when you listen to music or when you listen to conversation, sometimes the criteria, or actually many times, the criteria are different. But this is a good way to start with minimizing the mean squared error. So the solution, in our case, it looks like this. So the question is, how did we find it? So I hope you're familiar with derivatives. So what we need to find is actually, if we go back to the mean squared error, you see? So this is the expression for the mean squared error, you see? So in this expression, we assume that we know the variance of x. This is the variance of the desired signal in the input. And we know our x. This vector, I, is the identity vector, which is 1 and all zeros. And this is our y. We know the correlation matrix for the measurement, for the y. So you see, if we take this expression, we find the derivative. This is a scalar, right? If we find the derivative of this expression with regard to h and equate it to 0, we find the solution that minimizes this mean squared error. So this is a good exercise. How to find the derivative of this and equate it to 0. Okay, so if you're not familiar how to find derivative of such things, let me know, because you can find this on the internet, different formula. And this is, there are certain rules how to find the derivative of a function of a vector. Okay? If you're not familiar with that, it's very important to know these expressions. Okay. So the solution is like this. Ry minus 1, Rx, I. You see? So this is the vector, that's optimal. Now this vector, we can write it differently. We can write that Ry, we know that Rx, based on our model, is Ry minus Rv. Okay? So we can write this. We know that Ry equals to Rx plus Rv. So we can put, instead of Rx, we can put Ry minus Rv. So we get this expression, where IL is the identity matrix of size L by L. So my question is, suppose that I implement the Wiener filter and I find it from here or I find it from here. Will it be the same solution? So what do you think? It looks like the same, right? Okay. So when is it the same? When I know Rx and Ry exactly. If I know them exactly, so these expressions are the same. But if Rx is estimated and Ry is estimated from observations, so generally these two forms will generate different results. Okay? Because what I wrote over there, that Ry equals to Rx plus Rv, it's true for the accurate or based on the model Rx and Rv. But if Rx and Rv and Ry are estimated, if I estimate Ry from the measurement, this is not true anymore. Generally, it will not be equal to Rx plus Rv. So if I estimate, for example, Rv from periods where I don't have X, I don't have the desired signal, periods in time that I have only the noise, even stationary noise. And then I have some measurements. And this I estimate from a certain length of measurements. It will not obey this. And therefore, these expressions, if I use estimates of Rx and Ry, will not generate the same results. By the way, here I need Rx. Rx, many times it's very difficult to obtain. So the advantage of using this is that Ry we estimate from the measurements, and Rv we can estimate during pauses in the desired signal. Because the signal is, sometimes it's limited, it's not present all the time, where the noise is usually present all the time on interferences. But as I told you, this is very important information that we use, and if we don't have this information, we need to estimate them. And the estimation of Rx and Rv or Ry depends on the application, and every different estimates of these matrices will generate different results, different performances. And this is a topic by itself. Okay? We can also normalize Rv, Rx. So these are the normalized correlation matrices. Normalized correlation matrices, and we can use them, and we can obtain different expressions for the Wiener filter. We can also write it using the Pearson correlation coefficient. So this is Pearson correlation coefficient, or the squared Pearson correlation coefficient, which actually it's normalized correlation between two signals. So if we have two signals, Y and V, so this is the square root of the correlation divided by the variance of each one of them. So it's normalized. So it's in our case, it will be like this. So if we have a high signal to noise ratio, it means that this correlation will be higher or lower if we have high SNR. The more input SNR, the higher the input SNR. What will happen to this correlation coefficient? Higher or lower? Two options. I don't give like 10 options. Okay, only two options. So you can guess. You have 50% to succeed. Think for example, think Y equals to X plus noise. Okay? Y T equals to X T plus noise. So high input SNR, it means that this variance, X, is much larger than V. So the more they increase the SNR, it means that this ratio is higher. The variance of X divided by the variance of V is higher. So the correlation between Y and V will be higher or lower if we increase this ratio. Lower, okay? Okay, so we have a way to determine what is the signal to noise ratio. So instead of saying that the signal to noise ratio, the input signal to noise ratio is high, I can say that the correlation between the measurements and the noise is low. If I say that the correlation between the measurements and the noise is high, it means that the input SNR is low. Okay? What about the correlation between the measurements and the desired signal? So this is proportional to input SNR. If the input SNR is high, so the correlation between Y and X will be high. So this is the squared correlation coefficient, Pearson correlation coefficient, which is very useful. That's why you see here the relation between the squared Pearson correlation coefficient and the input SNR. You see, if the input SNR is high, it means that the correlation between the measurements and the noise is low. Makes sense. Okay, and for our example, it looks like that. This is the relation. But it's always true. It depends on the model. But here, it's 1 over 1 plus input SNR. So you can compute it. And what we can see that for the Wiener filter, if the input SNR goes to infinity, the Wiener filter goes to the identity filter, which is interesting. Because if the input SNR goes to infinity, it means that this is negligible. The noise is negligible. And then the Wiener filter goes to the identity, 1 and all zeros. It means that the estimate, Z, will be equal to Y. Makes sense. Because if the input SNR is very high, you don't need to do anything. It's better to keep the signal Z equals to Y, because Y doesn't contain much noise. But if the noise is significant, if the noise is significant, the input SNR goes to 0, so this is negligible. If Y equals to V. So H, the filter, goes to 0. Why? Because X is negligible. You don't have any desired signal. So it's better just to suppress the residual noise, because the mean squared error has two components. One is distortion, one is the residual noise. But the distortion is not important because you don't have X. It's negligible. So it's better just to remove or suppress the residual noise by equating the filter to 0. So you suppress everything because you don't have any signal over there. It's negligible. Okay? So these are sometimes when you derive something, you want to check that at the extremes it makes sense. The solution, your solution makes sense. So it's possible to check that. Okay. Another thing is, also it makes sense, we derived the Wiener filter that minimizes the mean squared error. This was our criterion. And we can ask ourselves, okay, we minimize the mean squared error, but what happens to the output SNR? Does it increase compared to the input SNR? Is the output SNR, so this ratio, the output SNR, the ratio from here to here, compared to the input SNR, is it larger or smaller? We didn't use any constraint or criterion based on the SNR. We just minimized the mean squared error. So it's very important to know. Because if it reduces the signal to noise ratio, we need to think, why does it happen? Is it necessarily increase the signal to noise ratio? So it's possible to prove that the Wiener, you see, with the Wiener filter, the output SNR is always larger or equal to the input SNR. So we don't reduce the signal-to-noise ratio, which is important. It's possible to prove it. I will not go through the proof. You can read, and it's straightforward to see it. But it's an important feature that the Wiener filter does not reduce the output SNR, because the SNR is also important. So this is the proof. Okay. And we can find, or we can write the minimum mean squared error. So we can ask, okay, with the Wiener filter, the mean squared error comes to a minimum. So we can write the minimum mean squared error by different expressions. And we can see that any mean squared error that is obtained with any filter, of course, it will be larger or equal to the minimum mean squared error, because this was obtained with the minimum with the Wiener filter. And also we see that we have upper bound for the Wiener filter, because if we take here the identity, we have the variance of the noise. So it's obviously the minimum mean squared error is smaller or equal to the variance of the noise. So we can see, if we use the expression that we obtained for the Wiener filter, we put it in the expressions that we obtained for the output SNR, the noise reduction factor, the desired signal reduction factor, and the distortion index. We get explicit expressions for all of them. Okay? Let's see an example. It's always good to see an example. Suppose that we have this signal, xt equals to A cosine 2 pi f0t plus phi. A is a certain magnitude, amplitude of the signal, is a certain amplitude of the signal. And what happened? Let's see. Okay. I don't know what happened, but okay. So suppose that we have this signal, and suppose that the amplitude is constant, f0 is lower than the Nyquist frequency, so it's between minus half and half, because t is the sampling interval. We assume it's normalized. Okay, everything is normalized. So the sampling interval is 1. We normalize by the sampling interval. And so f0 is between minus half and half. And phi is the random phase, uniformly distributed on the interval from 0 to 2 pi. Okay? So this is the desired signal. And suppose that we measure this signal together with additive white Gaussian noise. And we get the measurements like this. And from the measurements, we want to estimate this signal. So actually, in practice, if we know this model, if you know the signal, and the signal has some parameters, it's better to estimate the parameters of the signal and not the signal itself. Okay? So usually it's called estimation of parameters. So we will estimate the amplitude, we will estimate the frequency, and we estimate the phase. But here I assume that I don't want to estimate the parameters. I want to estimate the samples of the signals x from the measurements using the signals, using the Wiener filter. Okay? Obviously, I will get degraded performance. but I want to show you how to use the Wiener filter. Okay, so what do we mean? So if we take this signal and we have white Gaussian noise with variance sigma v squared, this is the input signal to noise ratio. You see the expectation. The only random variable is phi. This is random phase. So if we take the variance of xt is a squared divided by 2. So this is the input SNR. And we can also find the correlation matrix RV for the noise, which is sigma v squared multiplied with the identity matrix, L by L. So it's very easy. Why? Because it's white noise. White noise, it means that any element on this matrix outside the diagonal is 0. For white noise, it means that any two samples, which are not the same sample, okay? Any two different samples in the vector V are uncorrelated. That's why in the correlation matrix it will be 0. And along the diagonal, because it's the same variance, so we have sigma v squared. So this is the correlation, which is very nice here, because if we know that the noise is white, we put zeros except the diagonal, and along the diagonal, if the noise is stationary, so we can put the same value, and we can take certain measurements of the signal when maybe we don't have the desired signal, so we can estimate sigma v squared. Or maybe we know sigma v squared, so we put it here. So to estimate or to find RV, it's quite easy, right? In this example. Now, if we want to find Rx, Rx is more complicated. Okay, so maybe you can find Ry and subtract Rv from Ry based on samples of the measurements. This is one possibility. But here we choose another possibility, so which is based on, suppose that we know A and F0. We know the amplitude and the frequency of the signal. Usually we don't know that, because if we know that, we can estimate xt by only estimating the phase. But for the purposes of finding Rx, if we know A and F0, then this is an element ij in this matrix. So if I take two samples of Rx, of xt, and I take the expectation, because the phase is random, so this will be the expectation. Okay? So prove that. Okay? So I will give you today an assignment in this example. Based on this example, you will get an assignment. So I want you to understand this. So first, prove that I can find the elements. And also, suppose that I don't know A and F0, and I want to estimate this matrix from Ry. So I can find it's stationary. So I can take certain interval of yt, and based on examples of RT or the samples of RT, I can find any element of Ry, and then subtract from that Rv and obtain Rx. It will be different. Okay, so I want you to repeat this example and try these differences. I will continue. You see, it's not that easy even for that very simple example. Okay. And so for this example, I take A equals to half, F0 equals to 0.1, which is less than the Nyquist frequency. And sigma V squared is 0.3. So the input SNR is minus 3.8 dB. Okay? First, I'll show you what is the gain in SNR. The gain in SNR, which is the output SNR divided by the input SNR, that is obtained for different L. What is L? Remind me, what is L? The number of samples that I used for filtering. You see here, the number of samples that I used for filtering. So what I see here, that if I increase the number of samples, I improve the SNR. And I also, the minimum mean squared error using the Wiener filter decreases. This is very nice. It means that the more samples that I use, I improve both the mean squared error, it decreases, and the gain in SNR, it increases. Which is interesting. Is it always true? So why do we get here improved performance, gain in SNR and MMSE? The main reason is that we used Rx and Rv. We used the true matrices. So because these are the true matrices, when we increase L, we have more information. Because we know that within this vector of length L, we know the correlation, the true correlation between any two samples. And this is a cosine signal. So cosine, we know exactly the correlation between any two signals for a certain length L vector. So we have more information. If we increase L, we have more information. So we can estimate XT better. You see, that's why it increases. And this is decreases. Very well. But suppose that you don't know the true Rx and Rv. You estimate it from a certain length, and you don't increase this length. What do you think? What will happen? If we increase L, it will not necessarily increase. To some degree it will increase, but afterwards it might even decrease. Why will it decrease and not be plateau, or we stay at a certain level? Why do you think it may even decrease? Think about it. If the question is not, if you don't understand anything in the question, let me know. I will explain. Okay, so what I claim, that if we use the true Rx and Rv, the performance when we increase L increases because we use more information. But if we don't use the true Rx and Rv, we estimate it based on a certain length. The length of the signal Y is fixed because we have a certain length of information of samples that we use. 1 second, 2 seconds, 5 seconds, maybe 1 minute. And from that measurement, we estimate Rx and Rv. And then we increase L. So I claim that it increases, but maybe afterwards it may even decrease. Why will it may decrease? Yes. So what do you mean? So why will it may decrease? Okay, yes. So when I increase L, I put in the matrix Rx correlation between samples that are far from each other. And then I use this information. And maybe this information is misleading. It's wrong. You see, so when I use correct information, correct matrices, correct correlations, I increase the L, I have more information. But if I give you additional information, but it's wrong, because the estimates of these correlated signals which are far, maybe it's incorrect, then you will get error because of this wrong information, wrong estimate. You see, it's better not to use wrong estimates than to use it. Additional information, it's not always good. If the information is wrong, we don't know whether to use it or not, and we use the wrong information, so it leads us to wrong estimates. Okay? And this is well known in estimation theory, that when you use additional information and it's wrong, it's misleading, you get degraded results. So this is a very interesting. If you like, you can check it. Okay? So try something like that. Take a certain length of the signal and try it. So I will give the assignment soon, and I will talk about what is required. Okay, and here we get the output SNR as a function of input SNR, and the MMSE as a function of input SNR. You see that when the input SNR increases, of course, the output SNR also increases, and the minimum mean squared error decreases. This is obvious because we have less noise. And these are the noise reduction factor when we increase the input SNR and the distortion. So we see the noise reduction factor decreases. It makes sense because we have less noise, so we need to reduce less noise. And also we have less distortion. And also the distortion here, the distortion index decreases when we increase the input SNR. This is a realization of the signal. So suppose that we have a certain length. We have 500 samples of a noisy signal for that signal. So this is a realization. And this is the result of Wiener filtered signal. So first, because we apply Wiener filter, you see we don't estimate the amplitude and the frequency and separately, and the phase. So we get whatever we get. So it's the envelope here is noisy. It's not like one amplitude, and the frequency can change along the signal, and also the phase maybe it's inaccurate. But this is the signal that we get. At least it's better. The signal to noise ratio is higher. This is a realization with input SNR equals to 0 dB. So what is your assignment? So please work on this assignment. I will give you 4 assignments. Every 2 days, you get an assignment. Assignments are very important, not for the grade. It's just to practice, to see what you understand, what you don't understand. Okay, so first you have some things to prove, to show the mean squared error, some relations that we showed. It's very easy to show these relations. Another, so this is 1, another one is 2, is to show that taking the gradient of the MSE gives you this solution. And if you're not familiar how to take gradients of scalar with respect to vectors, you can find a formula on the internet. You will need that for array processing, image processing, deep learning. So it's better to learn that as soon as possible, okay? It's very useful to use this formula and to understand. If we take a gradient of a scalar with respect to a vector, the result is a vector. If we take a gradient derivative of a scalar with respect to a matrix, the result is a matrix. How it is defined. If we take derivative of a vector a function which is a vector with respect to a vector. The result is a matrix. Okay? So all these, what are the definitions? How do we define it? What is the element? What is each element of this matrix? So these definitions and how to find the optimality, vectors or filters and so on. This is like linear algebra. It's very useful in signal processing and machine learning. So people who are not familiar, please look at the internet on the formula, and I promise you that it's very easy. But you need to learn that. Okay, so here, prove the derivative. This is the solution. Number 3, show that the Wiener filter can be expressed like this, based on the squared Pearson correlation coefficient. Okay, so these 3 problems are very easy just to see that you understand, very basic. Here, the first one, this is using MATLAB, so it may take you more time to work on that. That's why I want you to use MATLAB code from my website. Okay, so I want you to generate the figures in example 1, all these figures that we just saw, but with different parameters. Change the parameters. Play with that. But I don't want you to spend now 3 days on that. Okay? So I want you just to play with the code, the MATLAB code, change some parameters, understand, and submit something with different parameters, and also explain what you did differently. And why did you obtain or you got different results with the different parameters, different estimation? You have time to play with that. It's up to you. Okay, and the figures, the figures in this book that I wrote, I'm co-author, so it's, the figures are different, so you can download the MATLAB code for all the figures in the book using my website here. So if you go to my website and you go to publications and you go to books, okay? So if you go to books, I have the books that I wrote. So this is the book for this course. And here you have partial solution manual for some of the problems, if you like. And also you have a MATLAB code for all the figures in the book, MATLAB code. So you can download it here. And then you need to know which figure in the slide correspond to which figures, because it goes according to the numbers of the figures in the book. So I tell you here that figures 2 to 5 in the slides correspond to figures 2.2 until 2.5 in the book. So when you download the MATLAB code, they correspond to this. For each figure, you have a MATLAB code. So you can play with it, okay? And then you generate different. So it's up to you how much time you invest on that. Any questions on the assignment? By the way, even beyond the assignment, things that you are not sure how to derive different expressions, so please try to prove it. Okay? And afterwards, so tomorrow, I hope you do the assignment today, because it's important when it's material fresh. If you don't have time today, it's also possible to do it partly tomorrow. But I want you tomorrow to tell me if something doesn't work, if you don't understand, so ask questions. Okay. And afterwards, we will talk about different filters, which are also important. We will talk about trade-off filter, MVDR, and maximum SNR filter. So trade-off filter, we will see, because the mean squared error, if we try to minimize the mean squared error, actually we minimize both the distortion and the residual noise. But sometimes we want to reduce more distortion on the account of increasing the residual noise, and vice versa. So we want some trade-off between distortion and noise reduction. So we will talk about trade-off filter. And then we will talk about MVDR filter. Remember, we talked about minimum variance distortionless response beamformer. We will use it. So we will show what is MVDR filter. What does it mean, MVDR filter? It means we want that X filter design will be equal to X, no distortion. And then we want to minimize the variance of the residual noise. This is MVDR filter. And we will see when we come to multi-channel signal processing, we will see the relation between MVDR filter and MVDR beamformer, or multi-channel MVDR. That's why we want to see it here. We will also talk about maximum SNR filter. We see that the MMSC filter, the Wiener filter, does not reduce the signal-to-noise ratio. But if we take the criteria, if we look for the filter that maximizes the output SNR, how different, what is the relation between the filter that maximizes the output SNR compared to the Wiener filter? Which one is better? Which one is better? The maximum SNR filter or the Wiener filter? Maximum SNR or min? Okay. So this is, you know, sometimes question is misleading question. It's whatever you say, it's not the correct question, the correct answer. Why? Because when I ask you what is better, you need to ask me according to which criterion, okay? So according to the minimum mean squared error criterion, Wiener filter is better. But according to the maximum SNR criterion, maximum SNR filter is better. So whatever is better, it depends on the performance measure. How do I measure what is better? And when I measure what is better, according to this criterion, I find the optimal filter, the same like beamforming, multi-channel, and so on. By the way, when you listen, suppose that I record speech in a noisy environment. Suppose that I show you pictures, and I show you a few pictures, and I ask you which picture is better. Or when you listen to signal, you listen to music, and I ask you which signal do you think is better? Okay? So there is something which is called mean opinion score. Mean opinion score. So this is many times subjective criterion. Subjective criterion that we try to optimize. We say that we listen to a signal, but then we need to take many people, large number of people to listen to signals or to see the pictures and so on. And we teach them to give grade to the signals. Sometimes the grade is 1, 2, until 5. 5 is the best, 1 is the worst. And then if we take a large number of people and they listen to the same signals or watch the same pictures or video or whatever, and we train them, we teach them how to give a grade, 1 or 2 or 5. Because if we don't teach them, they don't know that this signal, maybe it's 4 or 2, I don't know. but if we train them how to give this grade, and then we take the average grade for a large number of persons, it's called mean opinion score. So it's subjective. And many times we want to optimize this. For example, if I give somebody picture of X-ray, chest X-ray, and ask him, is it this picture or this picture? Both X-rays of persons, chest X-ray. Which one is better? But you don't understand which one is better. You need to be a doctor, or you need to be familiar with that. So you need to train which one is better and to get this opinion score. So you see, performance measures depend on the application. And when we try to optimize it, it's not easy. But here, because it's mathematically well-defined, we find the solution. So we will continue here with the other filters tomorrow, and then we will proceed. Okay? So any questions so far?